Okay, we want to talk about the determinant of a matrix. Now, the determinant of the matrix with row 1, 2 and row 3, 4, and you can only do a determinant of a square matrix, incidentally. The determinant of this square matrix, 2 by 2, is very simple to calculate. You just multiply the numbers on this diagonal, the 1, 4, and then you multiply the numbers on the opposite diagonal, 2, 3, and you subtract this one minus this one. So you have 1 times 4 for this diagonal, which I've kind of indicated with the light orange line and orange underline, times the product on this diagonal, which is underlined in purple here, the 2 and the 3, and with a little purple line here. I hope you can see the colors. Doesn't really matter because it's pretty easy to understand, but we just want to emphasize it. So we get 1 times 4 minus 2 times 3, which is negative 2. Okay, that's no big deal. Anytime you see a 2 by 2 matrix now, you can easily calculate its product. Okay, so let's say we ask you to calculate this product, or this determinant. Okay, what do you get? You calculate it. 1 times 4, there it is, minus this. Now you got to be careful because you're going to do minus this, and this already has a minus. So you want to put your minus sign down and then some parentheses before you do this. So minus the quantity, negative 2 times 3, and that's 10. Because of course this is negative 6, but negative 6 is plus 6, and 4 gives you 10. Nobody had any problem doing this. Now, I ask you to determine or find the determinant here. Okay, and gave people a couple of minutes, and they easily found it. They found that it was 2. Okay, because what? You got negative 4 here minus negative 6 here, which is negative 4 plus 6, which is 2. Now, there's actually an easier way to get this one. Okay? This first row here, well, let's compare this matrix with this matrix. What do you see? Well, hopefully, and pause for a second and look at it and make sure you see what there is to see. But what you see, if you see it, that's obvious, is that this row is negative of this row. So that when I multiplied the first row by negative 1, I got the negative of what I got when I did this matrix. Okay, the determinant is the negative of the determinant of this matrix. And it isn't hard to see because if instead of 1 and 2 I had negative 1 and negative 2, then I'd have a negative 1 here and a negative 2 here. That would change the sign of both of these numbers, which would change the sign of the result. So there we have it. So if I multiply a row by negative 1, it appears that I change the sign of the determinant. And that is true. It's always true. Now there's a more general rule, so it's not just confined to multiplying by negative 1, but we'll see it in a minute. So I say, does multiplying the first row by negative 1 always change the sign? And the answer is yes. Furthermore, if I multiplied, instead of multiplying the first row, I multiplied the second row by negative 1, well, that would also change the sign because now the 4 here would have the opposite change, and the 3 here would have the opposite change, opposite sign. So both the 4 and the 3 would have opposite signs, and that would change the sign of the result. Okay? Now, we calculate this determinant. Okay? And what do we get? Well, what's happened? How does this compare with this? Okay, this first row is related to this first row. How? Well, you've done enough row operations that hopefully you see that if we double this row, we get this row. If we triple the numbers in this row, we get this row. You might not have seen that. Depends on how quick you are at seeing those number patterns, but it's fairly easy to see once it's been pointed out. So I've doubled the first row and I've tripled the second row. What does that do? Well, if I double the numbers in the first row, that means the 1 here and the 2 that was here are going to become twice as big, and that alone would double my determinant. But I'm also tripling the numbers in the second row, the 3 and the 4. So if the 4 gets tripled while the 1 gets doubled, I'm going to get 6 times as much here, And tripling the 3 and doubling the 2 will give me 6 times as much here. So I'm going to get 6 times the determinant. So I've multiplied the second row by 2, the third row by 3. It doesn't matter which row I multiply by which number. I'm going to multiply the determinant by the product of those two numbers. Now, I state a simpler rule up here. If I multiply any row by some number C, fixed number C, I multiply the determinant by C. Okay? If I multiplied the first row by -1, we multiplied the determinant by -1. If I multiplied the first row by 2, that would make each of these numbers twice as big, and I would multiply the determinant by 2. Okay? So whatever I multiply a row by, the determinant is going to be multiplied by the same thing. Okay? Now let's try this one. How is this matrix related to this matrix? Now you can calculate the determinant. 6 minus 4 is 2. So the determinant is 2, and that's the negative of the determinant we had up here. But what is the relationship between these rows and these rows? Well, the relationship is fairly straightforward. I've just switched the two rows. And switching two rows, just interchanging the two rows, multiplies my determinant by -1. Determinant is -2 here. Switch the rows, get this. Determinant is +2 here. Okay? Another thing, okay? I've gone back maybe to the first matrix, or maybe I went to this one, I don't know. It looks like I went back to the first one. I reduced this matrix. How did I reduce it? I added -3 times the first row to the second row. Okay, if I do that, you can verify that this is what I get. And I take the determinant, well, it's just -2 here, and we don't get anything here. So the determinant is -2. So adding a multiple of a row to another row, in this case, didn't change the determinant, and in any case, it turns out this is a general rule. We won't change the determinant. I won't try to explain why here by hand waving. The other two aren't necessarily that difficult to see, especially multiplying by C. But these behaviors extend to any determinant, to the determinant of any square matrix. Okay. Now, in a minute, we'll talk about how to do a determinant of a 3 by 3 matrix.